Okay, so we are being recorded. Okay, so good afternoon again, and let's continue now where we left off. These first sets of lectures are really to set the tone and to get some basic understandings in about the signals and systems work that we're going to do. Right. So today, what we'll be focusing on, at least for the first part of this afternoon, is on some basic signal operations. Right. Signals can be manipulated in a variety of ways. For our purposes, some of the more important ways are time scaling, time reversal, and time shifting. And if you are like a Marvel Comics fan, there's like what Doctor Strange does, right? So let's see how this. There you go. This is how we do things. So the first thing is time scaling. Now, time scaling expands or compresses a signal along the time axis. And here's a question. Why would you want to do that? Why would you want to compress something along the time axis if it was possible to do so? Think of communication. The answers, those three answers are very, kind of going around the topic. But basically, if you want to compress a signal in time, what you're really asking the signal to do is to occupy less space. Now, think of transmitting files or transmitting images or transmitting data of some sort. The less space that it can occupy, the less time it will take to be transmitted from point A to point B. Okay? So, yes, in a way, you can make it go faster because it's taking less time. Right? But the main reason is just that bulky data, if there's some way that you can make it occupy less temporal space, then you're able to get it to wherever it's supposed to go in a much shorter period of time. But remember, in most things, if you compress it one way to make it take less time, then when it reaches its destination, you're now going to have to reverse the process, so it is restored to its original size. Somebody said to increase the frequency. Well, essentially that's what is done. And then somebody else, there was a comment there, not to go faster, to represent something larger on a smaller scale, not quite, to zoom out. No, that's not compressing in it unless you're talking about it zooming in a sort of time domain. But let's look at the example and then we'll clarify that a little bit more. All right. So take a function here. We have a function, it's some arbitrary function, 6 minus t squared over 2 plus t squared. Right. So it's a function of time. And we simply plot the function. You can do this in MATLAB or however you want. So you get the function, it looks like this. It's occupying some space in time, running from -3 to +3, maybe in seconds, okay? 3 seconds, maybe, we don't know. What we're going to do now is, let's find some way of replacing the t with 2t. So the function now becomes a function of 2t. So we now have 6 minus 2t squared over 2 plus 2t squared. And we plot that now together with the original signal. Right, so what's happened there? The green is the one where we replace t in 2t, and the blue is the original one. What has happened? Time-wise, what has happened? How much time does the signal occupy now? Right, the signal, well, technically, yes, it takes less time. It has been occupying. Now it's running from, let's see, we're running from this point to this point, right? So we're running at a little before at about -2 point something to +2 point something. Let's round it off. So approximately 4 time units, whatever that happens to be. Before, it was occupying a time greater than 6 units. The scale has been set to -3 to +3, so, but clearly it was going on even more than that, right? We just happen to plot it for that range. So what we've done is that we have taken something that is occupying 6 time spaces, and we brought it down to just over 4. And so what has happened there now, somebody used the term before, is that the same range of values of ft occupies less time than the original signal. It has been, in other words, it has been compressed in time. The flip side of it, of course, is if we take the t and replace it by 0.5 t and plot it, as you would expect, the 0.5 t, which is a red line, is occupying more time. In other words, it has been expanded for for people who know the term already. In this case, the TT. Hold the question, Jorel. We'll answer that in a second. All right. So the same range of values of f0.5t occupies more time than ft. It has been expanded in time. So therefore, if we want to do this operation, the way that you do it is that if you have a signal that is a function of t, you find a way of, in the signal, whatever is the t, you scale t by some function or some factor b, sorry. And if b is greater than 1, the signal is going to be compressed. And if b is less than 1, the signal is going to be expanded. Now this can be done electronically. There are circuits and there are systems, and you will learn it also in communication. First off, there are things called multipliers. Which are electronic circuits that take a signal and actually modify it by doing some electronic manipulation. In communication, you come across devices called mixers. And then on top of that, somewhere in there, you're going to learn about modulation. Right? Modulation is a prime example of this of the way you can take t and replace it by bt. Modulation, you multiply it by something, and because of the process of multiplying, you come up with something that is a different frequency, and you know it already. You know that for instance, from your trigonometric multiplication, trigonometric relationships in calculus, that sine 2a is 2 sine a cosine a, that kind of relationship, right? So you can see that if you multiply one by the other, all of a sudden you get a constant appearing, all right? Let's go on here. And this is to answer someone else's question from before about the frequency part of it. That if you take a signal sine and you have sine bt, and you have b less than 1 or b greater than 1, if b is less than 1, the signal expands. In other words, it occupies more time for a single period. So in other words, the frequency lowers. And if b is greater than 1, the signal compresses. In other words, the frequency goes up. And I think somebody in the chat mentioned that. Right? If I'm not mistaken, somebody did mention about increasing the frequency. Yes, it was there. Right? Somebody saying mod b, yes, yes, because yeah, you can multiply by -1 and you run into issues. But we'll get to that in a little while. That actually does something else, right? So, good point. And technically, mod b might be the better one. The constant mod b rather than a plain b. Right, and higher frequency, of course, translates not necessarily into well, it takes less time, yes, because it's varying more, but it also, if it's an audio signal, it sounds different as well. right? So you have to do something at the reverse end if that is what you're doing. Somebody writes, so Jordan asked the question, is it proportional as it increases or decreases? Okay, so what exactly is proportional? What are you talking about, Jordan? The amplitude?
The time that it takes is occupying in space. Like as it
But when you say
like you have 0.5 and it got larger, and then you had like 2 and then it got a lot smaller. So I just wanted to know if it was like proportional as it's like expanding using different values, or at the same
no, well,
rate.
that depends. Let's go back to the slide here a second, right? Let's put all three of them. Okay, so we have all three of them there. The function, it isn't proportional because the function itself, remember, it's a function of something squared, so it's not a linear, it's not linear. All right, so that the changes from one function to the other will not be a proportional change. If it was 6 minus t, for instance, and you replace it with 6 minus 2t, or 6 minus a half t, 0.5 t, those variations would have been proportional because t is linear, but t squared is not. Yeah?
Okay, it is. Thanks.
Okay, right. So where are we? Here. Right, so blowing of the SU here. Right, so consider this is supposed to be a discrete time signal. This is an example. This is almost looking like an echo. I tried reloading this thing and for some reason it's doing that. These are the results. Strangely enough, this is the result of Blackboard trying to take my presentation and make it available at the lowest resolution possible for everyone to see. So it's doing some signal manipulation here. It may be compressing, it may be doing something else, and then when it displays, eventually you get this funny thing happening looking like an echo. You have the handout, but what it's asking, so if you have a discrete time signal, n is running from -3 to 3, assuming that we the time period here, t equal 1 second, right? So what would be the values of nt? Well, if it's nt, then t is running from 3 to -3, and we're dealing with mod n. So the sequence of numbers, or the sequence of values that make up this discrete time signal will be -3, 2, 1, 0, 1, 2, and 3. And what does that look like? You plot it. If you plot it, then you have basically a series of points. The vertical lines are just so that you can align it with the what do you call it, the time axis, so you can locate where they are in time. But the actual information are just those blue dots on the screen. This particular way of depicting it is something called a stem plot that you see a lot in textbooks. And it also is a command because of how common it is. It's also a command in MATLAB as well. Right, so if you have for instance, if you were to go into MATLAB and you were to enter, just let xn be this series of values and tell it stem xnt, it will produce a plot that you're seeing on this side. Right? So what happened? What is the overall time of the signal? In this case, the time is fixed, so it's running from -3 to 3. If it happens to be seconds, this is running a total of 6 seconds. So you want to compress it to occupy half of the time that it was before. So what would the new spacing be there for? Between them, it's going to have to go, if we have to occupy it, if it has to occupy half of the time that it needed, the new spacing is going to be what? The spacing here, we want it, remember, it has to occupy half of the time. So if it has to occupy half of the time, it means all of these signals have to, right now it's occupying 6 seconds. If it has to occupy half of the time, it means that somehow we have to get it so that it now occupies 3 seconds. In other words, the spacing has to go from 1 second to 0.5 seconds. Yeah? So it will now occupy the 3 seconds. So if you do that, the spacing is now t over 2. And what we have instead of this blurry thing here is now x. Let me just get a marker here. We have x, let me try n 0.5 t. Right, so that's what the signal is now. We have to change because it occupies half the time. It means that the spacing has to go from t to 1 to 0.5. Okay, and this is what you're seeing in the red inside of here. So it occupies the space now is running from minus 1.5 to 1.5, which is 3 seconds. Okay, the amplitudes are unchanged. Notice that for the time being, we have not changed the amplitude at any point in time. So in this case, to compress a discrete time signal by some factor, the factor has to be greater than 1. And where you have the t in the discrete time signal, you have to replace it by t divided by b. And notice this here. Okay, it's the opposite of the continuous time case. And then you could consider, what do you want to do if I wanted to expand it by a factor of 2? All right, and this has to do with, in fact, how we got this signal in the first place. Remember, a discrete time signal is basically one that you get by, you take the continuous time signal, and remember we spoke about it yesterday, you sample and you get the discrete time version that we were just looking at. So you get the discrete. So if you want, instead of these things, if you want now, I sampled it at, let me just put slightly different color here. So I sample it at these intervals here to get the values. If I need to squeeze that, make it occupy less space, I need to squash this in. In other words, I have to sample it or look at it twice as much. That is why in the case of the discrete time, to compress, wherever you have a factor t, you have to decrease the spacing of the t. So when you compress, you divide, and when you expand, you multiply. Yeah? Fair enough? Okay, and here we have yet another blurry signal. So this particular one, look at this one now. This one, xn, and that's the convention. There sometimes when you hire handwriting, occasionally you might, instead of this, you'll see xn with the normal parentheses. We try to use square brackets for discrete time signals because it's almost like a linear vector of values, like a matrix of values. So we tend to use the square brackets. But occasionally when you're handwriting and so on, you will probably see it occasionally like that, simply because it's easier to handwrite, and sometimes when you're hurrying, you kind of don't notice. But from the time you see that it has a series of values in it, then you automatically know that this is discrete time. If it was continuous time, it wouldn't be like this. It would be a continuous function. Yeah. So in this case, xn is some function 1.5t plus this thing here. And if you plot it from -3 to 3, and you're doing it every 2 seconds, you get a series of values here. You plot this, these are the series of values, whatever it is. So what would it look like if I take n and replace it by 0.5, sorry, t, and replace it by 0.5t? Notice what I'm doing is just compressing or expanding. Am I compressing or expanding by doing this? Is that a compression or expansion? Well, it has to be one or the other. Let's take a poll. Right, remember what we said. If you want to compress a discrete time signal, wherever b is, you divide b by the factor. So if I divide by 2, which is a compressor, is the same as multiplying by 0.5. So I'm compressing the signal, and if I look here, notice that the signal now, instead of running from minus 6 to 6, we're now running from here, which is minus 3 to 3. Yeah? So this now brings us back to another little issue. Somebody pointed it out before. Notice what has happened to the amplitude. We've made it occupy less space. The signal has occupied less space, which is fine. Right, so we've gotten the compression, but we've also changed the amplitude as well. So the signal itself has changed. Right, it's not only compressed, but we've done something to the signal as well. So therefore, time scaling works only if the signal amplitude is not a function of time. If it is a function of time, then you're going to distort the signal. So what you send down the road is not going to be just simply the original signal taking up less time, but all of the amplitudes and values inside of them have also been changed as well. Yeah? Okay, so that's time compression, that's right, time scaling, if you like, time compression and expansion. What about time reversal? For continuous time signals, time reversal is equivalent to playing a file backward. So now with digital recordings and the like, you can actually reverse an audio file, right? Or you could play a movie. You have a movie on your phone and so on. You could reverse it, or you could look at it in the opposite direction if you like. In the case of a continuous time signal, that is where you are actually replacing the t variable with minus t. And in the case of the discrete time, you replace it n with minus n. And a practical sample of that would be reading a set of stored values from the last value to the first. So example, you have a device and it's storing numbers in it, a microprocessor for argument's sake, and it has been doing something, and inside of the registers, it has values. And instead of reading the values in the registers from the most recent to the first, you do it the other way around, and you read it from the oldest reading back to the first. Okay, so that's an example of time reversal. And when we come to talk about something called convolution, which we'll do early next week, this is the first concept you have to understand. What is time reversal? Right, and time reversal, as the image displays, if you take x, the one on the left-hand side, again, it's kind of blurry here, y equal 3 minus x to the minus 2. The variable here, so I'm using x instead of t, so if you like, instead of 3 minus x here, you could have 3 minus e to the, sorry, let me clear that. All right, 3 minus e to the t minus 2 here. All right, so e to the t minus 2, if seeing that we're talking about time, really should be a function of t instead of x, but it doesn't matter. If I reverse that, in other words, I take the t and replace t with minus t, this signal basically reverses in time. So wherever it crossed the axis here, you flip it around and it is mirrored around the t equal to 0 axis. Reversal in time basically flips the image around or flips the signal around the t equal to 0 axis. Okay, same thing for the discrete time signal. Here you have a series of values. This is the x. This is the x0 value. right here. So it flips everybody around that. So it's a mirror image around the x equals 0 value. Fair enough? That one is relatively simple to do. So if you ever faced with a signal and you have to flip the signal around, look at where the t equal to 0 axis, where the y axis in other words is. And you're going to, whatever it is going to be a mirror around the y axis. And more blurriness again. So what we want to do now is to shift. So shifting now, time shifting means moving the signal up and down the time axis as the case may be. So you're going to take t, you're going to take t and replace t by some new value, t minus some other value. It could also be plus, right? So t plus or minus some other constant. If tau is greater than 0, then what we have is something called a time delay or a lag. And if tau is less than 0, then what we have is a time advance or a lead. And I'm sure somewhere along your work so far you would have encountered lead and lag in your circuit theory, I believe it was. Like phasors, some phasors lead and lag and so on. Civil, Sadie? A lead and a lag? And this is also the second important concept for convolution. The first one, reversal. Yes, ECNG 1012 in the labs, right, exactly. Right? So the first concept here was time reversal, and the second concept now is time shifting. Current lead reversal, right? Exactly, right? And that is a time. A lead or a lag is a time variation. So if we were to go on here, these signals, as we have it, are continuous time shifting. So here I have the signal. Xt is tan minus 1, t minus 1. I have no idea where that signal would have come from, but there it is. If I were to, now instead of t minus 1, I have shifted it down here. You have the better one in your notes. So it's gone here, and we've gone, notice where the zero crossing is. The zero crossing before was plus 1. The zero crossing now is at plus 2. Right? So as far as the time 0 it is now happening further in time. Right? Before that zero crossing, the original signal, the zero crossing happened at t equal to 1. It is now happening at t equal to 2. In other words, it has been delayed in time. It's happening further along. All right? And then in the diagram below, instead of the zero crossing point, which is a useful reference point, the zero crossing point has now moved to t equal to 0.5. So in other words, the signal has been advanced, right? It has come up in time. Fair enough? So t minus anything, t minus whatever that is, the minus sign gives you the delay. Okay? And the positive gives you an advance. In the case of discrete time signals now, if you have the signal which is n, of the sample numbers m, n, and you replace n with n minus m, of course these are all integers, right? You can have a time shift by a fraction of a sample. Remember, the sample happens at particular intervals, so you can only move up and down depending on how fast you were taking those values. If m is greater than 0 again, it's called a delay. And if m is less than 0, you have an advance. And here's a discrete time version of it. So the signal at the top right, that is what the original set of values look like. If I delay it, again, notice where the 0 point has gone. The 0 point has gone here. In other words, it is one, it has been delayed by t, whatever t happens to be. T may be a second, it may be 2 seconds. In this case, in this one, it has been advanced. It's come before. So this one, the delay here is minus 2t. Sorry, the advance is minus 2t. All right? Fair enough? Everybody getting that? Now, the funny thing about it is that delays happen in electronic circuits all the time. And it's simply because things take time to happen. So in an electronic circuit, if you send, although you know things propagate at particular speeds, right? So you take a signal here and you send it down a fiber optic cable, or you send it by radio, the signal is still going to travel at the speed of light if it's an optical signal, but it still takes some time. So if even it goes at the speed of light, most of these signals and the sort of things that we look at happen so fast that even at the speed of light, a fraction of a second for some things is a lifetime. So you send something down and it's leaving here and it's going from here to Australia. That distance is enough for you to if you compare the signal at Australia to the signal that left here, you would see where the delay actually happened. Same thing for discrete time signals as well. So you send information across a computer network. By the time it reaches where it's supposed to be, just the electrical properties of the wires and the circuits and the switches and the digital components and so on would have caused the signal to delay, to be kept back by some amount. And even in the analog circuits, I mean, for those of you who are doing electronics as well, transistors, for instance, a transistor, no matter how well it's designed, it still takes time to switch on and off. So something happens and it still takes a fraction of a second to appear from the input to the output, which is where you get in things like the discussions. You may have heard the term already, things like slew rate, which is how fast the thing could change, right? So all of these things actually happen whether you want it or not. So we'll be talking about it sort of in a sort of abstract way by looking at it with a little bit of maths. The actual physical world does behave like this. Nothing happens instantly. So delays are there all the time. Advances are different issue. You can't bring things forward in time except relative to when you are looking at it. So if you have a recording like of this lecture, when you sit back and you record the lecture, you could jump into it at any point in time and you could go closer to the beginning, which will be an advance from wherever you are at that point in time, or you could go closer to the end, right? So you're free to move back and forth. So the advance really only works in the terms of stored information, or funnily enough, in the world of quantum physics. There are some strange things that happen apparently in that world, and the people who deal with that and relativity have some bizarre notions about time advance and time delays and so on. But we will leave that for them. Yeah, that's nice science, and that's where the nice science fiction stories come from. Okay, so here's the blurriest slide of the lot, which probably was the most important one of the lot. So it's how do you combine a set of operations? So you have a function g of t. Okay, forget this. Let's see if I can just clear up this a little bit. So kind of just rub away the thing here, right? So you have a function gt, and I have to pass it through. I'm going to pass it through some system, whatever that system happens to be, right? So remember signals and systems. So gt is coming in, and coming out, I have AG, right, T minus T0 over B, right? So the system, this system here is doing some sort of manipulation to the signal GT, and when it comes out of the signal, out of the system, it is now AGT minus TO over B. So what are the sequence of events? How do I process this operation? So let's see if we try it. There are a number of ways we can do this. So if I first take G and multiply it by A, right? That could be a gain, you know, that as a gain, like you go through an amplifier, it could be plus greater than 1, it could be less than 1. Anybody know what's the opposite of amplification? What's the term? There you go. No, attenuation is correct, not dampening. Right, the opposite of amplification is attenuation. So if A is greater than 1, you get amplification. If A is less than 1, mod A, I should say, is greater than 1, you get amplification. If it's minus 1, you could get amplification, but also it gets inverted. But if it's fractional, then you get attenuation. Yeah. So, okay, so the first thing, we take it, we go from G, we go to AG, so we amplify it. And then we take T and replace T by T over B. Okay? And then on the other side now, we delay it by, we delay T by T0. Notice the important thing here, and I'll highlight it for a little while. T. The important thing to remember in all of this is T. These are time functions that we're dealing with. So whatever we are, whenever we do the time scaling, we have to bear in mind that we are affecting the T function alone, not the T0, not the A. Okay? So if we do it in that order, so we amplify, or whatever it is, amplitude scale, then we compress or expand depending on the value of B, and then we delay T minus T0. We get the function that we want. If we did it in a slightly different order, however, we take G and we amplify it first, and then instead of compressing or expanding it, we delayed it in time by T0 first. So now at that point in time, we have AG T minus T0, and then we compress. Remember, the compression functions only affect T. It doesn't affect T0. So what will happen then is that B only is going to affect T. So what you're going to get is T over B minus T0. That's different. Now it's not what you want. So how do you correct that? If that were to happen. Look at the two of them. How can I correct it? No, I'm not talking about the order. I'm talking about if I have this. This is what I landed up with, right? I really want that. Exactly. So what you do, the difference between 1 and 2, right, is that 2 has been delayed by T0. If I were to delay it by T0 over B instead, then what will happen is that I'll have T minus T over B minus T0 over B, which is the same thing as before. So if I happen to do it in this order with the second process, to correct it, I have to change how much I'm delaying it by to get back the correct answer. Yeah? So in theory, both can give you the correct Both can give you the correct answer. But the first approach is the more foolproof approach to take. All right. So in other words, if you're given a process, you have a signal coming in and it's doing, the system has to do something to it, or you're being asked to do that. The sequence to perform them, first you magnitude scale, then you time scale, then you time reverse, and then last you time shift. All right. So your magnitude scale, which is here, that's not clear, the annotations. Your magnitude scale, all right, you compress or expand, and then you shift in time. All right. But look at the expression, or at the end of the day, what you need to figure out is if whatever you land up with, if that is giving you the same answers as what the original problem was. And we have some problems in the problem set, and I'll show you when we get to when we do some tutorials, some things that you can look for, so you'll automatically know if you ask to sketch something, if the value, if it makes sense, if you have done the wrong process or the correct process. Yeah. So your magnitude scale, your time scale, you reverse, and then you shift. All right. So, any comments on this section? Questions? Concerns? Is time the fourth dimension? Well, if you're dealing generally in the concept of what do you call it, physics, yes, they consider time the fourth dimension. So you have the three physical dimensions and time. That's how physicists tend to look at it. In our case, time for electrical engineers, time is just one of those things that we deal with. We couldn't care too much about whether it's a fourth or a fifth or a sixth dimension. It's just one of those things that exists for us, and we work around it and we work with it. Yeah. Any other questions on what we did so far? Very funny. Try Bitcoin. Okay, so I'll stop the recording for this part at this point, and let me just stop here.